In this problem, we want to determine the equation of the tangent line to the given curve at the point 0, 0. So first we need to remember a little of the algebra regarding how to write the equation for a line. Remember there's two forms for lines. There's the slope-intercept form, which is y equals mx plus b, and then there's the point-slope form, which is y minus y sub 1 equals my slope times x minus x sub 1. Now, it doesn't matter which form you use, but it's important to recognize that both forms require that you find the slope. We have to find the slope in order to write the equation for a line. And we know that the general formula for the slope is going to be the derivative. So essentially, we're thinking we need to find the derivative, which is going to be dy over dx. That's the derivative of y with respect to x, because that is going to give me basically a general formula for the slope at any point. So general formula for the slope, that's the meaning of the derivative in this context. Now, when we take a look at the equation that we were given here, we have to notice that we don't have y by itself. See, we have a mixture of x's and y's on both sides of the equation. So this is an implicit equation. We have not solved explicitly for y. That means we don't have y by itself. So that makes this an implicit equation, and that's why we have to use implicit differentiation to find the derivative. So that's the process I'm going to show right now. So when we take the derivative of both sides, we're going to write d over dx. That means I'm taking the derivative of everything that is on the left side of this equation. And then I'm also going to take the derivative with respect to x of everything that's on the right-hand side. And I'm going to really write this out one step at a time, where I know some of you are going to probably eventually start skipping some steps, but in this video, I'm not going to skip any steps. So we're taking the derivative of both sides with respect to x. Now, as we look at the left-hand side, we have to recognize that this particular expression here is a composite. This is a composite function, or it is a pregnant function, as we call it sometimes. So my outer function here is the sine of some quantity, and my inner function is x plus y. So when I compute the derivative of sine of something, I know that will be the cosine of something. And then when I compute the derivative of x plus y, again, I'm going to write this out in steps. We see that this is addition, so we're going to be computing the derivative with respect to x of each of these terms. So that's the derivative with respect to x of x plus the derivative with respect to x of y. And I'm writing it that way so that I recognize that when I do that implicit differentiation, I'm going to have to take the derivative of both of those terms. So let's go ahead and do that now. So the left-hand side, we're going to do the chain rule. Chain rule says we take the derivative of the outer function. So that is going to be cosine of something. And then what we put inside of this function is the original g function, the original inside, which is x plus y. So this is the derivative of the outer evaluated at the inner, is how we say that. That's f prime of g of x, the first part of the chain rule. And then we have to chain on the derivative of the inner. So now we have to work on chaining on the derivative of g. So this is where I'm using what I've written here. The derivative of g, since g has two terms, we have to take the derivative of each term. Now the derivative of x with respect to x is just 1. But the derivative of y with respect to x, since we don't know what y is equal to, we write that as dy over dx. So we're going to have 1 plus dy over dx. That's the derivative of the inner function here, which is x plus y. So we've dealt with the left-hand side of the equation. So now looking at the right-hand side, here, I'm looking at this underlined in yellow, I see again that I have subtraction, so I'm going to take the derivative of each of these terms separately. So that is going to be the derivative with respect to x of the first term, which is the 2x, and then minus the derivative with respect to x of the second term, which is 2y. So I'm going to erase my chain rule down here that I was just using to show you this. All right, so we have cosine of x plus y times the quantity 1 plus dy over dx. Now, the derivative with respect to x of 2x, since these variables match, that's just going to be 2. We don't have to do the chain rule there. However, this piece here, since the derivative with respect to x of 2y, we see that these variables don't match, this again requires us to do the chain rule. So the way I want you to think of this is we have an outer function, which is 2 times something, and then that inner function is that unknown equation we're calling y. Again, I'm calling this y because in the original equation, we did not solve for y. We didn't have y equals, some equation. So we don't know what y is equal to. We just know it's some unknown equation. Therefore, we're treating every time we see a y, we're treating it like it is a composite function. So the derivative of 2 times something is just going to be 2. And then the derivative of y with respect to x is our dy over dx. So to finish this off, we're going to have 2 times g prime, which is just dy over dx. And that is the derivative of the 2y portion. So now the calculus is really over and the rest of this is some algebra. And we have to recognize that this cosine of x plus y, this is one giant quantity, and it's being multiplied by a binomial. This has 2 terms. So we're essentially going to be taking this entire cosine of x plus y and distributing it into this quantity here. So that's going to be the cosine of x plus y times 1, which is just cosine x plus y, plus the cosine of x plus y times dy over dx. And that's equal to 2 minus 2 times dy over dx. Now at this point, we want to solve for dy over dx, and I'm going to underline my terms. So I have one term here, cosine x plus y. This is my second term. Then I have 2, which is its own term, and then minus 2 dy dx. So there are 4 terms all together. And the reason I'm underlining them is so that hopefully you can clearly see which terms contain a dy dx. So I'm highlighting those in green, and these are the terms we need to get on the same side of the equation. So however you want to arrange this, I'm going to bring the dy over dx terms to the left. So I'm going to have cosine of x plus y times dy dx. Then I'm adding the 2 dy dx term, since I'm bringing it from the right side to the left side. And then on the right-hand side, I still have that 2, and then I'm subtracting the cosine of x plus y over, because it did not have a dy dx. Because this is going to let me factor, so I'm going to factor out dy dx and be left with cosine of x plus y plus 2, which will eventually allow me to divide and solve for dy over dx. So we'll have 2 minus the cosine of x plus y, all divided by 2. Just kidding, there's no 2 there. That would be a cosine of x plus y plus 2. That's the 2. Okay, so we've done our implicit differentiation. And again, what this represents, what we have here, this dy over dx, is a general formula for the slope at any point. So now, going back to the problem that we were given, we were trying to write the equation for the tangent line at the point 0, 0. So the way you can notate this is draw that vertical line and put the coordinate down here. Now, if we didn't know the y value, we would have to then take the given x value, plug it back into the original equation to find the y value. But in this problem, they gave us both x and y. So now we're just going to substitute in 0 for x and 0 for y. So cosine of 0 plus 0 here over the cosine of 0 plus 0 plus 2. So essentially 2 minus the cosine of 0 over the cosine of 0 plus 2. Now, using your unit circle, thinking about an angle of 0, which is going to be right here. If we're looking at our unit circle, this coordinate on the unit circle is 1, comma 0. And since we're looking at the cosine of 0 degrees, we know cosine is going to be the x value. So cosine of 0 degrees is going to be right here, and it's going to equal 1. So we'll have 2 minus 1 over 1 plus 2, which will be 1 over 3, 1/3. Now again, the meaning of this number that we just found, this is the slope at the point 0, comma 0. So to finish this up and actually write the equation for the line, we're back to two options. One option is slope-intercept form, y equals mx plus b. We know that the slope here is going to be 1/3. So that would be 1/3 times x. And then it just so happens that, remember, the b value is the y-intercept. And in this case, since the point that I was given was 0, 0, and you know that the y-intercept is always going to be the point where x is equal to 0. So since x is equal to 0 here, this point 0, comma 0 actually is the y-intercept. So that's like having a y-intercept of 0. So you could actually use slope-intercept form to write the equation for this line. Or if you're a person that likes point slope, you could have also used point slope form. So again, we're looking at the y value of the point is 0. The slope is 1/3 times x minus the x value of the point, which is also 0. But we can see if we simplify that, that certainly simplifies down to y equals 1/3 times x. So this is the equation for the tangent line. It's the equation for the tangent line, specifically at the point 0, 0. So just remember, anytime you're writing the equation for a tangent line, you need a point and a slope. And the way we're going to get the slope is by computing the derivative.